here we go. This is our lesson on projectiles. I'm going to deal with this in two situations. First of all, I'm going to deal with an object that's displaced horizontally from a high height, and we're going to look at that motion, and then we're going to take a look at motion that's being projected at any angle. So we're going to look at the horizontal projection. Okay, first of all, we need to imagine a ball that is projected at a speed horizontally. And so long as there's no acceleration, and this is going at a constant speed, that ball will continue to move, displacing an even distance each for the same time period, continuing to travel at velocity v. Superb. Now this is unaccelerated, so this is constant motion, unaccelerated. So therefore you can have very simple equations that we're familiar with at GCSE, that being that the distance covered, displacement covered, is going to be the velocity multiplied by the time period. Excellent. Now let's instead imagine that that ball is sitting on a very, very high cliff, and we're going to consider what happens to this ball, another ball, if you were to drop it. And if you were to drop it initially, then the ball would start to fall, but just like our ticker tapes, as it would fall, its distance would start to increase because the ball is picking up speed, it's accelerating till we get to this point. Let's say down here. Okay then, so now with a horizontal projected ball, what happens is our object is simply a superposition of these two states. So we have the actual position of the ball is where it's the position at which it would be horizontally and vertically. These two have to be considered independently, which means that the motion of the ball is parabolic. There's lots of different demonstrations to show you that actually the velocity of this ball in both instances vertically is identical. Slightly increasing in speed, increasing a bit more in speed, increasing greatly in speed, and finally with the fastest speed at the bottom. However, this ball will still have the same horizontal component as the ball at the top, because the only force acting on this is gravity, and so therefore the only acceleration that takes place is that which is in the vertical plane. So what we do is we resolve this horizontally and vertically, and then we solve necessary problems. So bear in mind that vertically you can use all of the Suvat equations. The two most useful are v squared is u squared plus 2as, s is ut, half a t squared. Fantastic. So let's try and work out then for this object some interesting values. Let's first of all work out how long it takes for that object to hit the ground. Okay, so let's first of all work out the time it takes to hit the ground. Okay, the only thing that's going to control when it hits the ground is actually how fast it is accelerating vertically. So therefore we need to just consider this vertical aspect of the object's motion. And in order to do that, anything moving vertically makes use of the Suvat equations because it's accelerating. So for this example we're going to use s is ut plus half at squared. Initially, vertically, it's not moving at all, so therefore we can ignore this part of the equation. And of course it's falling under gravity, so that becomes g. So therefore s, 2s over g becomes our time period square rooted. Quite a useful little equation there. And in all the equations you're going to deal with, if you're able to work out the time period, you will be always able to work out the range of this motion. And when I mean range, I mean how far this object has moved horizontally before it's come to rest by hitting the ground. So let's work out the range as the second one. Well, the range is very, very straightforward. If we move back to look here, because this motion is constant and unaccelerated, the distance moved is going to be the velocity multiplied by the time period, the time it's taken to hit the ground. So therefore, the distance is going to be the velocity multiplied by the time period. We already have an expression for the time period. So therefore, this expression becomes our range. Superb. Now, even though the vertical velocity matches with both the object that's being projected horizontally and that which we're falling in a straight line, the actual velocity of this object will, of course, be slightly greater because it has this horizontal component. And the way that we work out the actual velocity is by using Pythagoras. We'll be able to work out the horizontal and vertical components, and if we add them together, we will be able to find out the overall velocity of the object at any point in its motion. Let's show you what I mean. Let's take this example, for instance, when it strikes the ground. Here's the ball. It has a horizontal velocity which is identical throughout all of the motion, and its vertical velocity here will be merely the use of this equation. V vertical is going to be the initial vertical velocity plus the acceleration times time, and of course this is 0. So our vertical velocity is going to be the acceleration times time. So therefore, in order to work out the actual velocity, let's call it A, it's horizontal, we just use a simple Pythagorean identity. And therefore, we can work out the velocity at which it strikes the ground, or at any point in its motion. Similarly, if we wanted to work out its angle to the horizontal, then you can imagine this part of the motion is actually the same as if we were to draw the arrow there. And so this time now we have our vertical velocity as our opposite angle, our adjacent is the horizontal velocity, and therefore we have an identity which is tan of theta, which is our vertical velocity divided by our horizontal velocity. Theta thereby is tan to the minus 1 dV over VH. Excellent. So that's all the theory there. Let's put that into practice with a question. And once I've set up the question, you might want to pause it so you can give it a go before you see my actual solutions. Okay, so here we go. Nice simple example of an object on a tower again. The tower is, let's say, 76 meters. The ball is thrown off at 3 meters per second. I think I've got one of these examples which I've probably given you in class. They talk about a rock star throwing a TV out of a hotel window. That's why the speed's not particularly fast. Anyway, what we're going to work out is we'd like to work out how long it takes for the TV to hit the floor, so the time. We then want to work out the distance that it is covered as it strikes the ground. So if you want to give that a go first, hit pause, give it a go, However, I'm going to go straight on with the solution. Okay, we know, once again, the acceleration, just for convenience sake, I'm going to write as 10 meters per second every second, i.e. g, rather than 9.8, but you might need to use 9.8 for reality. Because I'm looking at what's happening vertically, I can say s ut, that's the initial vertical speed, plus a half gt squared, because it's dropping down. Of course, initially, there is no speed to it at all, so therefore my time period is a very simple rearrangement. And I'll put some values into that. 2 pi 76 divided by 10 square rooted gives me, I believe, 3.9 seconds. Okay, that's how long it's taken to hit the ground, so therefore if it's continued to move at 3 meters per second horizontally, then the distance, let me just write time up there so we don't confuse, and the distance is going to merely be the velocity multiplied by the time period. 3 by 3.9 gives us 11.7 meters. Okay, really straightforward. Let's work out something else. Let's imagine the TV finally hits the ground. We want to work out the actual velocity it's hit the ground with and the angle to theta. So we're going to work out the angle and the actual velocity. Okay, then to solve that, what we need to do is, first of all, we need to work out its horizontal velocity, its vertical velocity, and then we'll do a bit of Pythagoras to work out its actual speed and the angle at which it was travelling at when it hit the ground. Horizontal velocity is easy, that's 3 meters per second, because we said the motion stays constant as it goes across, as it goes horizontally. The vertical is going to be the initial vertical velocity plus the acceleration times time, which, once again, we know it because it's been projected horizontally. It has no vertical initial speed, so therefore this becomes gt. And our expression for g is 10, and our time period was 3.9, so that gives us 39 meters per second. Okay, the velocity, I'm just going to move it across here so we have a bit more space. It's going to be using a bit of Pythagoras. It's going very fast vertically, but that's because it's not really moving much at all horizontally. It's just crashing down. And that sets us up with 39.12 meters per second. Just take a note there, it's actually moving faster than it would do an object that drops straight down. That's because we've got some horizontal component. And finally, theta is going to be, if I move that vertical arrow across here, which I know is 39, tan of my angle is the opposite over the adjacent. So my angle is tan to the minus 1, 39 over 3, leaving me with 85 degrees. In actual fact, it's moving pretty vertically. I haven't really drawn the picture to very good scale. Okay, so that's horizontal projection. It's a much simpler way of, it's the first way of looking at things because our horizontal velocity stays nicely constant. Okay, and let's look at our second condition, which is if an object is projected at any angle. Okay, we're going to work from the ground. And once again, it's exactly the same as the first instance, but this time we have to consider the vertical motion that's slightly more complicated. Let's just imagine that this object, though it's being projected at v at an angle theta, will have a vertical component and a horizontal component. Pretty sure you intuitively know that it's going to do something like that. And I suppose if we clear the easy bit out of the way first of all, because it's going at a horizontal velocity which is unchanging, we know that for similar time periods it's going to be travelling an even amount each time. And this velocity is unchanging, just like the first instance. However, vertically, its initial vertical velocity is very high, so therefore it's going to cover a large distance initially, a decreasing distance, an even more decreasing distance, I don't know why the ball's got smaller there, and then it's going to stop, and then it's going to retrace its steps as it comes back down again. Vertically, we have g acting on it, so once again, anything vertically has to obey the Suvat equations. Anything horizontally is just constant motion. So once again, these are the resultant positions of the ball. I'm going to put another one in there just so I can show you it's got to the top, of which there is this dual component of the horizontal velocity, which is constant in all cases, but the vertical velocity is reducing until there is no vertical velocity at the top, and that's really important. And then the vertical velocity starts to build again until it strikes the ground, moving at the same velocity but in the opposite direction in which it started. Okay, so what's going to be interesting here is, first of all, how do we work out that vertical velocity component, and how do we work out that horizontal velocity component? Well, it's pretty much the opposite to what we did in the last instance. If I just redraw this to make it a little cleaner, here is our velocity, which is often given, and we have a vertical velocity and a horizontal velocity at an angle. Our identity here is we know the hypotenuse of this right angle triangle, and so therefore if we know the opposite and the hypotenuse, it's a sine function. Sine of theta is going to be our opposite over our hypotenuse. Therefore it's not hard to work out that our vertical velocity is going to be v sine of theta. For the horizontal function, we have our horizontal and our adjacent, so therefore we have a cosine. And with a small rearrangement, we can see that our horizontal is a cosine of that function. Superb. Now there are three things that we really need to be able to work out confidently with the situation above. And I think one of them is the time of flight. The other one is the maximum height. And finally, the range motion of that object. Let's tackle each one of those on its own. Okay, first of all, time of flight. There's two ways of doing it. Let me just show you the first way of doing it. We're working out how long the ball has taken to go up to the top of its motion, to stop, and then to come back down and strike the ground. The vertical component dictates how long the ball is in flight for. So therefore, we can use the Suvats in the vertical component, and I'm going to use this one. S is ut plus half 80 squared. Now, two things here. These are very powerful equations so long as you keep the get the numbers right and the symbols correct. If I'm looking for the time of flight, it's taken off at 0. This is a displacement, so therefore I'm looking for when it's come back to 0 again. Displacement of 0. So we have 0 is ut plus half 80 squared. My u, which is vertical, is going to be v sine theta t. And then because g is acting in the opposite direction of motion, we've got a half g t squared. Because I've got a 0 on this side, I can get rid of the t's quite happily. And my time will therefore come out to be v sine theta, 2 lots of it, divided by g. So that's my time of flight. Excellent. Okay, for the maximum height, we'll come back to the second solution in a minute. But for my maximum height, what I'm interested in is once again working vertically and knowing that at the very top of its flight, it's going to have no vertical velocity anymore. So therefore, for the maximum height, I can use the kinematic equation in which I'm looking just vertically again. And I know that at the top you have no speed whatsoever. Initially, I have v sine theta. And once again, g is acting against the motion, so I need the minus sign there. It's not hard to make that rearrangement and come out with the equation v sine theta all squared divided by 2g gives the max height. Fantastic. Now let me just bring you back briefly to the time of flight. If I know the height at which it's, if I know that it's going at 0 vertical velocity when it reaches the top of its flight, then I can use this identity, vertical, which I know it's going at 0 at the top, and I know it's initially going at v sine theta minus gt, because the acceleration is opposing the motion. And so therefore t here is going to be v sine theta over g. To get to the top and to come back down again, I'm going to require 2 lots of it to get me back to the same equation as before. So either way, it's just as good. And I suppose finally, working out the range, which is the really easy bit, is knowing what the horizontal velocity is. The range is going to be the horizontal velocity multiplied by the time, which gives me v cos of theta multiplied by 2v sine theta over g. Now that might look complicated, but in actual fact you'll be given values and you won't actually have to get to this type of derivation before some numbers have gone in. However, I would just say here, for those of you that are feeling more competent about it, what is the maximum range possible, what is the angle required to give the maximum range possible? So really, if we differentiated with respect to theta and equaled that to 0, what would theta be? I'd like to try that. Give that a go. Okay, let me set up another problem. We'll give that a go, and you can see if you want to solve it before watching my solution. Okay, here we go. Very simply, we have a simple sort of CCF that has a gun, and that gun fires a shell moving at 100 meters per second. Just guessing there, but I think that sounds reasonable. And then I want us to work out the maximum height. let's call it h, max. I want the time of flight, and I also want the range. Okay, if you want to press pause here and then give that a go yourself, or carry on through and I shall show you my solution straight away. I'll take this a little faster to start with. Right, so time. Okay, we are going to look at its vertical speeds, and its vertical displacement. I know that I'm looking for when it hits the ground again, so its displacement is 0. Its initial vertical speed, because these are verticals, will be 100 sine 30. Whilst I'm here, I might just put in its horizontal speed is going to be 100 cos of 30. So therefore, 100 sine 30 minus a half, because its gravity is opposing it. Let's get rid of the t's, gives me sine 30. There is a minus sign there, but I'm about to divide it by a minus g, which gives me a positive. What's this going to be? This is that's a half, so therefore I've got half of 50, but times by 2 gives me 100 over 10. So that's going to give me a 10-second flight. Okay. Let's look towards the height. We are going to look again vertically and say that the vertical final velocity is going to be 0 at maximum height. Of course, my initial velocity is 100 sine 30 squared minus 2gs, minus because it's opposing the motion, so it's 100 sine 30 squared minus, I've moved it across, but divide that by minus 2g, gives me a plus, which is s, 50 squared over 20 should give me 125 meters. That's how high it's gone. Time, 10 seconds. So therefore, what's the range? Well, the range, remember, which is the easy bit. It's the velocity horizontally multiplied by the time period. The velocity horizontally is 100 cosine of 30 multiplied by the 10 seconds, which gives me 866 meters. Excellent. Okay then, right. I think it's probably worthwhile, now I've done all those, I think it's probably worthwhile leaving you with a question. This question is not quite as straightforward. You have to do all of this before you get rise to the answer, so it's going to require a bit. But anyway, this is the question. Let's imagine, again, we're using a gun. I'm interested in what speed do you need to project the missile if you're trying to cover a range of 15,757 meters. And I suppose I should have said throughout the whole of this, this is of course frictionless, but what is the speed required in order to achieve that value?